Today we're doing 1.3. We're doing representing and describing transformations. So a transformation is where you start out as one thing and then you change and you become something different. In the case of geometry, we need some terminology to describe this. So we're going to say that the original thing is the pre-image. So pre meaning before, just like in books you have prequels to the original book. So this pre-image is our original point, point A, and then we apply a transformation and it becomes the image. Think of an image as like if I were to trace something, that would give me an image of it, right? Not exactly the same, it's been changed a little bit. We also have another term here, so if this was point A, this is point A with the little tick mark, and the little tick mark means prime. So I would call this A, and this, the pre-image is A, the image is A prime. And that's true of any point that gets a transformation. Finally, we have this thing called coordinate notation, and that's where we list out our x value and our y value. So here's our example of coordinate notation. It's right here in purple. X, y becomes, through the transformation, x minus 4 and y minus 3. So Will, can you tell me what 0 minus 4 is?
-4.
-4, good job. What's 4 minus 3?
-1.
4 minus 3 is -1?
1.
Yeah, just 1. So A, which starts at point 0, 4, becomes A prime at the point -4, 1. So that's over, oops, that's over here. We're going to come down 3 and over 4 to right there. Similarly, point B, what is 3 minus 4, Will?
-1.
Good job. And then what is 0 minus 3?
-3.
-3, good job. Okay, and we'll do the same thing with point C, and that'll give us points B prime and C prime. Note that all of these points move the same direction and same distance from the original pre-images, right? So this transformation is a specific type called a translation. So don't get too confused. There's two different terms there. One is transformation, where something just changes in general. And then one of those types of transformations is called a translation. And a translation is where we simply slide left, right, up, down. The orientation is the same. The size of the shape is the same. The shape itself remains the same. So size and shape are preserved in a translation. Okay, we're going to do another one here. In this one, we take our x value and our y value, and what do we do to it? Well, we simply make the x negative. So we multiply it by -1, right? In this case, point R is at -4, 3. So what's it going to become after the transformation, Millie? Does the y stay the same?
No.
The y? I have y here and y here, so that stays the same, right?
Yeah.
Yeah, so that stays the same. What do I do to the x? I have to make it
Negative.
but it's already negative. So what's a double negative? A double negative is a, do you know this?
Positive.
Yeah, positive. So that's a +4. So a -4 is a +4. So that gives me 4, 3. Similarly, -1, 3 becomes 1, 3. -4, 1 becomes, what's a -4?
4.
Yep, +4. Awesome. And then we can graph those. And when we graph them, it becomes clear that what we've done is we've reflected it. That's the official term for this, this transformation is a reflection. And you can see why it's a reflection. You can think of this y-axis as like a mirror, right? It reflects from here over to here. Is the size the same? Yes. Is the shape the same? Yes. The orientation is different, but it's the same size and shape. So we're just gonna note that it's the same size and shape. Okay, finally we have this one here. What's different between these two, Will?
One is xy and the other is 2xy.
Yeah, so what are we multiplying by the x?
Times
Yeah, so we're multiplying this x by what number?
2.
2, yes. So we multiply our x values by 2. You guys can figure out the x values. You can multiply them by 2. Whatever. You don't need to do this step if you're doing this on your own. So what is negative 1 times 2, Willie?
Negative 2.
Negative 2, good job. All right, and then we just bring down the y values. And so this gives us this transformation. Let's see what happens to it. It becomes, whoa, look at that. So we started with the skinny triangle, JKL, that's our pre-image. And then we got a fatter triangle, it's wider, right? This would be a horizontal stretch is the term here, because we've stretched it horizontally by a factor of 2. In this case, it's more or less the same location. Is the size and shape the same? Does it have the same size and shape as the previous triangle? Does the pink one and the gray one, are they the exact same size and shape?
No.
No, they're not. The pink one is bigger and fatter, right? So it does not preserve size and shape. Okay. The ones that preserve size and shape, we have 3 of them, and they're called rigid motions. We have translations, we have reflections, and we have one more mystery one that's coming up. And yeah, mystery, super mystery one that's coming up. And all 3 of those rigid motions, they preserve size and shape. That's pretty much all you need to do to think about what a rigid motion is. Okay, in this one, we're actually going to do the same sort of deal, but we're going to do it backwards. So we're going to start with our transformation. You even could be given the values, and our goal is to figure out what the pattern is, right? What is the transformation? And then finally, they want us to just confirm that it's a rigid motion, that length and angle measurements are the same. So in this case, we look and we try and figure out the pattern. So we start with A is 1, 2. A prime is negative 2, 1. Do you see that, Willie? How they start here and then they become like this. So point B, I'm actually going to make a little shade here for that bottom one. So point A starts at 1, 2, and then A prime becomes negative. It becomes negative 2, 1. B is at 4, 2. It becomes B prime at negative 2, 4. So what did they do to each one? What's the pattern, do you think, Will?
They had it so the front 2, so they switched the places.
They did switch the places. Good observation.
And then they made the left side into negative.
That is an excellent answer. I am so impressed. All right. So they switched the places. So XY becomes what? YX, right? And then you said they make the first one negative, so it becomes a negative YX. Let's see what happens. Let's double check it and see if it's right. So if C is at 3, negative 2, what would that become?
2, 3.
2, 3. Good job. You got it. Nicely done. Okay, so we've figured out our transformation here. And as it turns out, this is a rotation. This is our mystery third one. So it preserves length and angle measurement, but we got to prove it. So the way they're going to prove it is they're going to use a protractor to measure the angles and estimate the angles, because right now that's the tool you have. But we can do a little bit better than that on lengths. So if we were to check the lengths, what is the distance between, say, A prime and B prime? How far apart are they? Well, we can just count it. 1, 2, 3. They're 3 units apart. How far is it from A to B, Willie?
3.
3 units apart. Good. We have to get a little fancier when we go from like B to C. That is 1, 2, 3, 4 squared plus 1 squared, square rooted. So the distance from B to C is the square root of 17. The distance from B prime to C prime, 1, 2, 3, 4, down 1, is also square root of 17. And then finally, A prime to C prime, right? This one is over 1, 2, 3, 4. So 4 squared plus 1, 2 squared. That's 16 plus 4 is the square root of 20. Same deal here. A to C is the square root of 20. So if we were to in order to confirm that this is a rigid motion, we check all the side lengths. We show that all the side lengths are the same, and then we can use just a protractor to figure out the angle measurements and show that the angle measurements are the same. Okay, we'll go ahead and walk through B here. If you want to pause and do this yourself and then check your work real quick, feel free, but I'm doing part B here. We're going to do the same thing. We're going to figure out the rule, and then we're going to apply that transformation. We're going to check to see that it preserves length and angle measurements. So go ahead and pause if you want to try this yourself. We can figure out the rule is xy becomes x negative y, and then we can confirm the length and angle measurements. And I'll just give you all these fill in the blank things. You don't really have to fill this in. I don't grade you on taking notes, but it may help you to test yourself and then confirm later. So the question is this a rigid motion? Well, we can check the angles, 37, 37, 56, 56, 87, 87. All the side lengths are the same. Therefore, yes, this is a rigid motion, or preserves all the lengths and angle measurements. Okay, go ahead and do 5. We'll pause right here. So go ahead and try this on your own. I'll take this away in just a second. Pause the video. Okay, so hopefully you got the rule, negative x, negative y. And for number 6, hopefully you got the rule plus 1 minus 2. Right? The first one here they both preserve length and angle measurements, and you should be able to prove it using the distance formula, or the distance of the sides. Okay, it's actually in some ways easier to confirm that something is not a rigid motion, because all you have to do for this is show that one pair of angles isn't equal, or one pair of sides is not the same. And remember, this happens on transformations that are basically stretches, left, right, up, down. It doesn't work with our rigid motions of translations, rotations, or reflections. So we'll do a quick example. In this case, we can see how the pre-image maps to the image. What do you think the pattern is here, Will? You think you can figure it out? Let's just look at the x's. We start at -2, and then we become -4. We start at 4 and become 8. We start at -2 and become -4. So what are we doing to the x values?
We're making the negative.
Well, they started negative, right? -2 became -4. So it stays negative, but we multiply it by a number. What number are we multiplying it by? 4 times what number is 8?
2.
2, yeah, it's twice. And then what about this one? 2 becomes 1, 0 becomes 0, -2 becomes -1. No, and the minus doesn't work because we go from 0 to 0. So it's not a minus. We're actually dividing by a number. What are we dividing by? 2 becomes 1. 0 becomes 0. Negative 2 becomes negative 1.
Multiply?
We're dividing by something. 2 divided by what number becomes 1? If I have 2 cookies, how many people do I have to divide that among so everybody gets 1 cookie?
2.
2, yeah, 2. So it's half. We're putting in half, right? So our rule is multiply the x by 2, multiply the y by 1/2, or divide the y by 2. If we check the lengths of mn and m prime and n prime, we get square root of 40 for mn. We get a different value for m prime to n prime. So therefore, we can stop right there. We don't have to check any of the others. We can just say, hey, look, these aren't congruent. They're not equal. Therefore, it's not a rigid motion. Okay, see if you can do 8 or 9 real quick. So again, pause here, and then do 8 and 9. I'll put my hoodie up. Boink. Okay, so hopefully you figured out the rule of multiplying by 3/2, basically. And it's not a rigid motion. You can prove this in myriad ways. Don't worry about it. Just have one way to prove it. Similarly, this transformation is you multiply the x by 1/2, and then you multiply the y value by 3. And again, you can pick any like pair of sides. You could graph it and use angles, but really we can just use distance formula. Okay, that's it. That's all I got. Have a good one. Say bye, Will.
Bye.